So just remembering, when you do electron configuration, you need to know the total number of electrons. Electron configuration is based on number of electrons. So it's not based on atomic number, and we need you to remember that. So shortcuts for writing electron configuration, just knowing where it stops, right? So you have row 1 and row 2 are called the S block. Row 1 is going to stop at S1, and the N, it's going to stop at what I call NS1, and the N corresponds to the row number, or the period number, but I like to call them rows because why do we have to be complicated and call it a period? So in row 1, going across, it stops at 1S1. In row 2, we stop at S2. So if I pick calcium, calcium is in row 4, then the last thing written on the electron configuration is 4S2. And then for the transition metals, that's D block. We're not really going to be dealing with that, although you may be asked on an exam to write the electron configuration for a transition metal. One thing that I won't ask about is one thing I won't ask about in the D block is what I would call the fourth column in the D block or the ninth column in the D block, because those ones are weird. All right. And why are those ones weird? It has to do with the Hund's rule and the pairing of electrons and the Aufbau principle and energy levels. You talked about that in Gen Chem 1. I'm not going to focus on it here. Let me look. Let's get the... Why isn't it working? Okay, let's get the laser pointer out. All right, so what we do in the D block, this is the transition metal block. It is group 3 through group 12 on this periodic table. Or if you look at the periodic table that I use for class, we call this, the transition metals are groups 3B through group 12B, okay? So 3B through 12B, and these are going to be D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. Okay, so as you go down a group, it's going to end at a different number of D. And then the number that precedes the D is actually going to be the row number -1. So scandium would end its electron configuration at 3D1. Manganate would end its electron configuration at 3D5. Let's see. I don't like doing gold and silver and stuff. Those are weird ones. Cadmium in row 5 would end its electron configuration at 4D10 because it's in the 10th row of the Ds and it's in row 5, and 5 minus 1 is 4, so it ends at 4D10. When we get over to the P block, that's usually pretty simple. Instead of calling these rows 13, 14, 15, 16, and 18, I call them 3A, 3B, 3C, 3D, 3E. Whoa, what am I saying? That's crazy. Okay. 3B, 4B, 5B, 6B, 7B, and 8B. Yeah. So the reason that we do the AB grouping on the other periodic table is so that the group number corresponds to the number of valence electrons. So P1 is group 3B, P2 is group 4B, etc. And that is where the electron configuration will end. So you have row number Carbon is row 2. It ends its electron configuration at 2p2. 2p2. All right, good deal. And then when we will only very moderately cover atoms that can exceed an octet, and usually only when we're writing out Lewis structure of polyatomic ions such as phosphate and nitrate and etc. And the reason that we would have those sulfate, phosphate, nitrate ions is as reagents that change our carbon compounds. Our carbon compounds are not ever going to break the octet rule. I won't even talk about the F block because it obeys the same rules. You have F1, F2, F3, F4. And we don't deal with those atoms in this class. Okay, so this is the periodic table that I will give you on your exams. Or if we're in person, this would be the periodic table that you would have. And so number of valence electrons, what you're going to do is you're going to use the group number. The group number will correspond to the number of valence electrons on your periodic table. I will share this periodic table in the files for the course so that you can have access to it. You can print it out, you can save it on your computer, whatever you need to do in order to have access to it. But you need to memorize certain group numbers. You need to memorize certain valence electron numbers. The ones that I have memorized that I use all the time are hydrogen, carbon, nitrogen, oxygen. Those are the most important, and the halides. Those are the most important ones. I know carbon has 4 valence electrons. I know nitrogen has 5 valence electrons. I know oxygen has 6 valence electrons. And I know the halides all have 7 valence electrons. And the way that I use this information is in knowing how many bonds are going to go to the atom and how many lone pairs are going to be on the atom when we have a neutral molecule. So if we have a carbon as a central atom, it has valence electrons of 4. It needs 4 electrons to form an octet, and therefore it will make 4 bonds, gaining 4 electrons, because carbon will own half of each bond. So we have 4 valence, we bond to 4 things, we get up to a total of 8 valence electrons surrounding the atom. Nitrogen, it has a valence of 5. How many electrons does it need to get to an octet? 3. Nitrogen prefers to form 3 bonds and have 1 lone pair. Oxygen has a valence of 6. Guess how many bonds it's going to make? 2. 6 plus 2 equals 8. It's got its octet. But if only 2 bonds, each bond has 2 electrons, that's a total of 4 electrons. So where are the other 4 electrons? In lone pairs. So it'll have 2 bonds and 2 lone pairs surrounding oxygen when it's a central atom. Fluorine, halide. Halides make how many bonds? 1. 7 plus 1 is 8. So halides will be bonded to one other atom and have 3 lone pairs. So continuing on with our discussion, atoms in the first column of the periodic table tend to lose an electron. So we're talking about formation of ions now. If we're in group 1, we lose an electron. You should all know that formation of cations. If you're on the left side of the periodic table, it's easier to lose 1 electron than it is to gain 7. So we lose 1 electron to become like the noble gas on the previous row. So lithium, which is in row 2, becomes like helium in row 1. So it will become like the noble gas helium. In terms of number of electrons. Valence electrons. Sodium, which is in row 3, will become like neon, which is in row 2. So metals tend to lose electrons to become like the noble gas on the previous row, the row up one. Okay. Anions are formed from nonmetals, and the nonmetals are on the right side of the periodic table. And so it is closer for a nonmetal to gain electrons to become like the noble gas than it is to lose electrons. So fluorine can either lose 7 electrons or it can gain 1. Gaining 1 electron is easier. So when we gain an electron, we become negative, we become an anion. And so nonmetals tend to form anions. They gain electrons until they have the same configuration as the noble gas at the end of their same row. And then they will have a negative charge because the number of protons is no longer equal to the number of electrons. Hydrogen atom can gain or lose an electron, and we're going to be dealing with both in terms of reactions in this class. Hydride ions can react and protons can react. By the way, why is it called a proton? Because there's no electron and no neutron. Hydrogen does not have a neutron. So hydrogen has atomic number 1 and mass number 1. When atomic number is equal to mass number, there are 0 neutrons. And when we lose our electron, then the only thing left is our 1 proton. 0 electrons, 0 neutrons. All we have is a proton. Therefore, we can call a H plus ion a proton. Okay, something else that I want to mention, isotopes of hydrogen. Yes, you do need to know this. Yes, it is going to come up, and you will probably be annoyed. When we write out the isotopes of hydrogen in organic chemistry, we write D for what we call deuterium. This is a hydrogen that has a mass number of 2 and an atomic number of 1. For the other isotope of hydrogen, the radioactive isotope called tritium, we write T, and this is equal to a hydrogen that has a mass number of 3, atomic number of 1. So deuterium has how many neutrons? 1 neutron. Tritium has how many neutrons? 2 neutrons. This is the H-bomb form of hydrogen, by the way. Radioactive. Okay.